So Graeme West from Strathclyde University, who some of you may remember his father, Tony West, who was my boss at Sheffield. And he's still there, I believe, Graeme.
He is, yes. He'll never retire, I don't think. So, yep.
Yeah, there's a joke about faculties and academics, isn't there? But anyway, Graeme, over to you to tell us about digital technologies for AMRs.
Okay, so the usual question, can everybody see my screen?
Yep.
Yep, great. Okay, so yeah, thank you for the invite to speak at this this very interesting workshop. What I'm going to talk to you today about is digital technologies in a broad sense, but in a sense, most of this has already been covered through peppered through the various preceding presentations. So that's really made my job a lot easier. So in terms of what I want to talk to you about, first of all, just really what definition of, or what my definition of digital technologies is, and where it's applicable, and then look at some of the challenges specifically around digital technologies for AMRs, and then go on to look at some of the opportunities as well. Okay, so in terms of digital technologies, it's a broad catch-all term. Loosely defined, it might be the disciplines of electronic and electrical engineering and computer and information science, with strong links into related disciplines, and usually, though, many of the disciplines use the results. Use data analytics, use digital devices, so a whole breadth of things. I tried to distill down some sort of definition here. So a digital technology might be some codified digital analog of the physical world, gathered, stored, and used by humans to better understand the physical world. And this understanding may lead to decisions or actions. But when I was defining that, obviously there's things like analog is a nice confusing term for us. We've got digital versus analog, so maybe representations is maybe a better description. When we talk about gathering the information, then traditionally that might have been through wired, but we've now got wireless technologies available. So we might be looking at the opportunity for wireless in here. And then when we start talking about the decisions that are being made, I've put in there made by humans, but as we're going towards more autonomy and more autonomous systems, then there are opportunities round about there for either computer-assisted decisions or maybe fully autonomous decisions. So that's kind of setting the scene, and that's what I want to talk about in this talk. So, where are digital technologies relevant to AMRs? Well, really, it's across the board, through the full life cycle, from initial feasibility and design. They can help support the understanding of fundamental principles, and they can be used in things like simulations to provide evidence, through to the next stages of manufacturing. So modern manufacturing techniques using digital enabled technologies. But also importantly, and I think this is a thread that will run throughout, is that when you're manufacturing your components for your AMRs, you're going to be generating information about how and in the forms that it was created, and there's going to be data associated with that. So if we're looking at data technologies across the whole piece, then we need to look at things like the provenance of the data as well. So things like blockchain technologies might come in to give us that assurance that the information that you're getting from the manufacturer that then is moving through to the to the operation and to the use, you've got that tie through. Areas such as training, we've got technologies, virtual reality, augmented reality are big at supporting those sorts of activities in modern industry. And then when we come on to the operation of your stations, we've got a big piece around control and instrumentation. These new designs and new approaches will also require new sensor technologies, and underlying that, that's really how you get from the physical world into the digital world. So qualification and design of these new sensors is going to be important. And there's also opportunities in terms of when you're operating the reactor to introduce optimal performance and efficiency through leveraging the data that you're gathering as you're operating the stations. And also, there is an opportunity here for a step change or a different approach to the way that we might, if you like, traditionally control and monitor and operate stations, as we can gather more and more information in real time about the online state and the online health of the plant. And of course, there's the big role of safety as well within that whole process. And then coupled with the online monitoring, we've also got offline maintenance. So if you're taking the plant offline and inspecting, and again gathering more information that's feeding your digital twin or equivalent of the online plant, I guess the digital version of the online system, there are opportunities round about there. And then also looking towards sort of future operation and lifetime extension of the plant. And one of the previous talks mentioned that they weren't considering that in terms of the here and now, in terms of some of those decisions. But I think there is a wealth of experience we've had from the AGR programme in terms of being able to retrofit and being able to install new monitoring and inspection devices onto our existing operating plants in order to support extended and future operations of the plant. But there is an opportunity there, right there, that if we think about this up front, if we think about how we're going to monitor these items of plant and build in the digital equivalent from the start, then maybe we can foresight and maybe we can lay the foundations for easing that opportunity for lifetime extension in the future. And importantly, it's not just the reactor systems themselves, but it's the full fuel life cycle and secondary systems. I alluded to that within the manufacturing, but there are challenges here about being able to share data and share data openly within the closed sort of supply chain of the nuclear industry. Okay, so moving on to some challenges that I see. Okay, one in particular is the pace of evolution in digital technologies. So I've got to give credit here to my 4-year-old son here for the picture of the tortoise and the hare. But digital technologies is your hare. And harking back to, I think it was the first presentation of today by Lawrence, where he gave a quote from Sir John Hill, who was talking about the pace and the change over that 10-year period. If we reflect back, and here I don't want to cause offence to maybe some of my colleagues that do some of these other areas, but if we look at something like concrete, really, if we look back to 1985, and here's a picture of the pressure vessel wall being prepped, the underlying processes of concrete haven't changed significantly over the interleaving years. On the right here is Hinkley Point C's concrete foundations being poured. Yes, there's been big advances there in terms of being able to do that at a bigger scale and more efficiently, but fundamentally the concrete's kind of looks the same as kind of doing the same sorts of jobs. If we look at steam generating turbines, again, manufacturing technologies have moved on here, and materials have become better, but fundamentally they still appear very similar. But if we look at the digital world, back in 1976, if you look at communications, here's a screenshot from an episode of Blue Peter, from 1976, where they demonstrated this new device, a mobile telephone, where you could wander outside and speak to somebody on a landline. And then fast forward to today, the iPhone 12. It's an astronomical difference from what was perceived there in 1976. And remember, in 1976, that's when Hunterston B came online. So after this, I would encourage you to go away and have a look at that link, but do so on your mobile phone. So that's a whole sort of another layer of meta that you're looking at the advancements on technology on the technology. Similarly, we'll look at things like data storage. Again, back in the 70s, that might have been pen plotters. Interestingly, some of the data there is part and parcel of your station records. It's a requirement to record some of that information and then have it held physically within a secured fireproof building on site. Fast forward to 2021, and the ability to gather and store vast volumes of data has increased incredibly. We're now in the age of the cloud. So, but with these new technologies, there comes the new threats. There's new vulnerabilities. We need to build in resilience to things like cloud-based solutions. We can't be losing 20 years worth of operating records because a web service goes down. Similarly, we'll look at things like AI and machine learning. Going back even further, here's an early example of what was AI back in the 60s, and this was a computer psychologist program, a psychotherapist program, which was intended to mimic how a psychotherapist might interact with a human being. It was very simplistic, and really all the AI did here was to take whatever you typed in and then reframe that as a question back to you. But we're now living in the age of the digital voice assistants, of your Siris and your Alexas, and that step change has been absolutely phenomenal. So, just looking at another sort of case study, and this is some of the research that we've been involved in, up at Strathclyde. This was to do with inspecting some of the graphite cores. So in the early days, they used to send cameras into the core, have a look around, and then any cracks that were discovered, they would effectively digitize the images and then hand draw the representations of those. And then moving through the paces, we were able to retrofit some digital technologies onto the original footage that was captured, to where we get to the present day, which is a system which builds up a full internal picture of the fuel channel walls. And then skipping over to the right, that's where we start to look at the art of what is possible. So this is using some 3D point reconstruction from taking sort of the latest advances in 3D point cloud technology. Okay, so drifting on to some specific challenges around about these digital technologies. There are, and these are specifically sort of instrumentation and control challenges. But we have problems which haven't really been addressed in terms of the use of microprocessor-based digital technology. Back in the day, we were very happy with analog, and we knew where we were with analog. There's been that sort of halfway house of field programmable gate arrays and hardwired logic-based digital technology, but there's still require for an increase in the diversity and defense in depth. So a lot of these technologies which have been adopted by other industries, there's still a challenge remaining within the nuclear sector for adoption of these, and a lot of that is around about the ability to fully 100% understand all the processing that's done with, or all the processing that's possible with these digital technologies. So there's a big challenge round about that. Other areas in terms of introduction of wireless communications, and there are a couple of major fields there. One round about cyber security. Again, with hardwired systems, you need to physically get access to the plant in order to to disrupt that. Whereas wireless is a lot more vulnerable to different forms of attack. In terms of how far we can look at automating the process, well, we've got explicability of decisions. We've got major advances in the AI and the data analytics field, but a lot of those are black box technologies, neural networks, which provide you with an answer, but they don't give you the underlying explicability of those decisions. And then there are some challenges around data integrity and retention. Okay, so just to really finish off, there are a number of opportunities that I can see, and that's one is building technologies into the design. It's into the full life cycle of the process. So that's from everything from the new sensors to the new ways of storing the data itself. A few of the previous presentations spoke about the need to capture that underlying knowledge as well as just the data, and having a common way or a common platform to allow you to exchange that information, I think is going to be incredibly valuable. Again, we can look back, and the first session was about looking back to history. A lot of the work that I've done, if you had those sets of commissioning data or the understanding of the decisions that were made back at the commissioning of the AGR stations, that would help us a lot in terms of the decisions that we're making now. The last point here is looking at full through life economic modelling as well, in order to realise some of these benefits with increased automation. That will drive down costs, and perhaps there's an opportunity there not to just look at the operation of the reactor in isolation, but look at that wider and bigger picture there. Okay, so to summarise, I think digital technology is really that thread that runs through a number of these areas, and while this presentation has been slightly different from I guess a lot that we've seen today, it's still important to consider, or I feel it's important to consider this in isolation as an issue that needs to be addressed. And from my perspective, digital is not just about the algorithms, but it's about pulling this whole system together in order to leverage and to be able to benefit from some of the advances that have been done. Okay, thank you.
Thank you, Graeme. Very thought-provoking, great pictures. Can I suggest that we now move into the discussion session, and any questions for the speakers from this future-looking session can roll over into that. So, Andy, I think I will hand over to you to chair the discussion.